Hello. Today we continue our discussion on wind energy, and in fact we will wind up our discussion on wind energy. We will sort of wrap things up with today's class. And in the last few classes we have looked at the whole wind energy concept and the area from a wide range of different perspectives. So, we looked at economic aspects, we looked at geographical aspects, we looked at environmental aspects, scientific aspects associated with it, and technological aspects. So, you really have to look at all these aspects to get a much more complete feel for the field when you make a decision, long term decision on any particular technology. So, for example, I also told you, this long term is a very important thing, and the idea of looking at a technology from its starting point to its finishing point is also another very important aspect whenever you are discussing any kind of technology which you want to put out as a mass market application technology. So, for example, we discussed specifically about the blades for the windmills and the fact that they are presently being made out of composite materials. So, it is very important that the composite material have a pathway for eventual reuse or recycling that is somewhat reasonable, that you can do without creating a situation where the amount of chemicals being used and maybe perhaps wasted or released into the environment during just the manufacture of the windmill being so high that it destroys the purpose of putting a windmill up there for clean energy. So, this kind of what they refer to as cradle to grave kind of analysis has to be done with any technology, not just windmills, just any technology, because often the first thing that we see about the technology often looks very promising, and that may also be a good thing to notice. But then we have to do this kind of analysis to understand if there is any other aspect of the technology where you need to tighten up, and it may just be quite possible that once you identify that problem you can solve it, and then after that the technology right from the beginning, the cradle stage to the till it is finished off and has to go for recycling, that entire life cycle of that technology is a clean life cycle, and then you really have made a big difference. So, that is the kind of point of view we have to take. So, with respect to wind energy, as we said, it is clean because it is just wind, it is already there, you are not really burning anything to create this energy or any such thing, it is already there, and in many ways it is a variation of the solar energy, because the solar energy heats the atmosphere, and then you get these various densities at various locations of the atmosphere, and then you have a weather pattern that develops, and based on that and location of plains, location of hills, mountains, etc., you have pathways for wind, and so accordingly you can tap the wind energy. We saw how the amount of power in the wind depends on the cube of the velocity, and therefore high velocities are very nice. And we also saw these issues, like I said, about how the blades are manufactured, how the tower is manufactured, and that the various materials are being looked at for all of these things. The idea that you can use permanent magnets, but then you need to have a lot more of neodymium, which may not be easy to get. So, all these issues have to be looked at as a totality to completely utilize that technology, to be aware of what is the weak point, so that you can simultaneously keep addressing that weak point, because it is also true that you may never find a technology which has absolutely no weak point. So, you will have some weak point, you have to be aware of it and keep addressing it as you go along, so that it is no longer a show stopping weak point. It may still be something that is not the best that you are expecting it to be, but it will not be something that people will look at some years down the line and say you should never even have taken this path, right. So, that is something that we have to be aware of. So, as I said, if you are going to put out hundreds of thousands or millions of windmills out there, then it is important to know what is the path for recycling those blades, because if you put out a million windmills, and if they are all 3 bladed windmills, you have 3 million wind blades that are out there, windmill blades that are out there, that you have to do something about once they complete their life cycle. And these are very long blades, these are 60-meter blades, maybe 70-meter blades eventually will come. So, these are long objects, these are not some small things that you can pack and hide it away somewhere. You have to deal with them, you have to do something about them. So, that is an aspect that you have to look at. So, in today's class we will actually as I said sort of wind up this discussion on wind energy. In particular, we will look at some things associated with some overall design considerations for the windmill, and see what sort of thought process is involved there, what kind of options are there. Maybe we are not fully aware of all those options, So, that kind of an discussion we will have, a little broad based discussion which puts some perspective on the technology as a whole. Okay, so our learning objectives for today's class are to differentiate between lift and drag designs of windmill. So, this is something that we have briefly discussed actually in one of our earlier classes, that first of all that there are these variations in the design. So, although you see a windmill and you just see something moving as a result of the wind that is blowing, there is a large amount of difference that exists between one type of windmill and another type of windmill in terms of the ability of that windmill to effectively capture the energy available in the wind. So, all of them will capture some energy. It is not that they were not going to capture some energy. If as long as there is something that is stable and has a predictable or consistent way in which it moves, we can always attach a generator to it and then tap that energy, and that is basically what is being done. But for various considerations they may have done one design versus the other, but each design has some specific advantages and disadvantages, and in that context there is a difference between what are considered as lift based designs versus drag based designs. So, we will look at that. The other thing that maybe sometimes we think about, but maybe we do not really look at in any great detail, is to understand the significance of the number of blades that are present in a windmill. So, I mean we traditionally tend to see 3 bladed windmill designs, but what are the options there, and why do people why most of them are sitting at 3 blade design. So, is there some great significance to it, or is there no significance to it, is it simply a matter of symmetry, things like that. We just need to get a sense of what is involved here in terms of the significance of the number of blades, and also alternate designs for wind energy capture. Okay, so, there may be lot of interesting other designs that people are looking at. So, we will at least consider one which is significantly different than what we have discussed in the class so far. In some ways it is significantly different, it is actually fundamentally there is something similar. So, I will highlight that to you, but in some ways it looks significantly different. So, we will see that as well. So, we will look at differentiating between lift and drag, we will understand the significance of the number of blades that are present, and we will also examine alternate designs for the wind energy capture. Okay. So, these are the learning objectives for the class, we will just see them as we go along. Okay, so in this context there is a term that I actually defined a while earlier, but we did not discuss it in detail. So, I will highlight that here. It is called the tip speed ratio. Okay, so, tip speed ratio, it is something that is reasonably significant in the context of windmills or wind turbines, and we should at least get a sense of what it is, and maybe how it can be used to consider possibilities with respect to a wind turbine. So, it is in terms of description and mathematics it is relatively straightforward. We are basically looking at the ratio of the linear speed of the tip of the blade. Okay. So, linear speed of the tip of the blade to the wind speed. So, it is a ratio of 2 speeds, the speed of the tip of the blade of the windmill to the ratio to the speed of the wind itself. Okay. So, what do we mean here? So, for example, you see a schematic here of a windmill, right. So, you see a schematic of a windmill. So, let us say based on how the breeze is blowing, let us say it is rotating that way. Okay. So, let us say it is rotating this way. So, if you take if this is the way in which it is rotating, if you take the tip, this tip of this blade, this specific blade, and that will be true for all the other blades, there will be a certain velocity with which it is moving. Okay. So, there is a certain, so that velocity we are referring to as V tip, V subscript tip, that is the velocity with which the tip of the blade is moving. And why is it moving? It is moving because there is wind coming from the front and moving backwards, right. So, wind is moving from the front of this windmill and moving backwards. So, going past the windmill and going backwards, and we will assume that the wind is coming horizontal. So, the windmill is standing there, and then the wind is just blowing this way. So, blowing past the windmill and then continuing further. So, there is a velocity with which this wind is coming towards the windmill, and because of that this windmill is rotating, right. So, this windmill is rotating. So, we want to know as it rotates. So, for example, if these are the windmill blades, if they are rotating, we want to know what is the velocity of the tip of this blade. So, what is the velocity of the tip of this blade is something that we want to calculate, and then having calculated the velocity of the tip of the blade, we divide that by the velocity of the wind that is coming, and that is referred to as this tip speed ratio. So, that is basically what we have put here, represented by lambda. It is the ratio of the tip velocity, which is the V tip that I have up here in the numerator, divided by V wind. Okay. So, this is what we have, and if you look at angular velocity versus if you look at RPM of something that is rotating, you look at how many radians per second it is going through this angular motion, then the linear velocity of that of any point based on this due to this, as a result of this angular velocity, is simply V equals omega r, where omega is the angular velocity and r is the radius of the point, of that point for which we want to know what is the linear velocity, right. So, if you have a longish blade and it is rotating, so you can consider various points here, you can consider a point here, you can consider a point here, you can consider a point here. So, I will just say this is A, this is B and this is C. So, even though omega is the same, if the whole blade is rotating round and round and round, and omega is the same, so many radians per second you will have the angular velocity. The linear velocity of each of these is going to be different. So, if you look at this formula omega r, V equals omega r, clearly the r is more. So, this is I will just say this is r1, this is r2 up to here, let us say that is the center, r1, r2, so I will just clear this, that would be r1, this would be r2 and this would be r3. So, clearly the linear velocity of C is higher than the linear velocity of B, is higher than the linear velocity of A. So, Vc is greater than Vb is greater than Va, and that simply got to do with the fact that to travel the same angular movement, to make the same angular moment, the A had to travel a less distance, B had to travel longer distance, C had to travel even longer distance. So, as a result, and that has happened in the same amount of time. As a result, the linear velocity of A is less than the linear velocity of B, is less than the linear velocity of C, even though they all have the same angular velocity, right. So, so this is V equals omega r, and so if you want to know the velocity of the tip, once you know the RPM of that windmill, you just have to sit there and watch the RPM of the windmill, then you will know how many radians per second it is revolving at. So, full 360 degrees would be 2 pi radians. So, based on that, how many RPM it does, that many RPM into 2 pi radians it would have covered in 60 seconds. So, you get the angular velocity, and once you get the angular velocity, you do V equals omega r, and then you get the linear velocity. So, if you do that, you will get this lambda, which is the tip speed ratio omega r by V wind. Just to give you an idea, and we are going to see some values as we go along. We are looking at lambda values which could be, lambda could be less than 1 in some cases, based on the design of the windmill it could be less than 1, lambda could also be greater than 1, it can of course also be equal to 1. So, it can be less than 1, greater than 1, etc. So, you are looking at a range of values, and usually I mean maybe towards the higher end of the spectrum we are looking at something like lambda could be approximately say maybe 6 or 8, okay, or maybe even 10. So, something like that is what we are looking at as the value of lambda in the normal set of circumstances that you are going to see a windmill in, and for a set of types of windmill that you are going to consider. Okay. So, that is the tip speed ratio, which means what? I mean we need to understand what it means by 6 or 8, or what is the significance of saying lambda is less than 1 or lambda is greater than 1. If lambda is less than 1, it means that the tip is moving at a speed linear velocity which is less than this velocity of the wind. Okay. So, please remember at least with respect to the type of windmill that I have shown you on this plot, which is this 3 bladed windmill, the wind is actually flowing perpendicular to the blades, right, it is flowing perpendicular to the blades. So, the tip of the blade is moving in a direction perpendicular to the direction of the movement of the wind. Okay, so they are not in the same direction, they are in perpendicular directions. So that is something that you have to keep in mind. Okay, so they are moving in perpendicular directions. What we are saying is when lambda is less than 1, the blade, the tip of the blade moves with a velocity that is less than the velocity of the wind that is crossing that blade. Okay. So if the velocity of the wind crossing the blade is, let us say, 10 kilometers an hour, or let us say we want at least 10 to 16 before this thing starts moving, let us say it is moving at 20 kilometers an hour. So it may be moving at 20 kilometers an hour, the tip of the windmill is perhaps moving at 15 kilometers an hour. Okay. So in that case you will have 15 by 20, so 0.75, right. So that would be the ratio if you had something like that, if the tip were moving at and so we will assume 20 kilometers an hour breeze, and then relative to that we will think about it. Supposing you had 20 kilometers an hour breeze, whereas the tip was moving at 30 kilometers an hour, then you would have 1.5. Okay, so 1.5 would be the lambda value or tip speed ratio. And if you have something like, when I say 6 to 8, so what does it mean? When it is at 6, it means the wind is flowing at 20 kilometers an hour, the tip is moving in a direction perpendicular to the wind. Please remember that it is the direction perpendicular to the wind at 120 kilometers an hour. Okay, so that is the point that we have to remember. So you may wonder how come that velocity is higher than this velocity, but that has got to do with the fact that the phenomenon that is occurring is different, and that is the reason there are some designs where it is where exactly what you are thinking is going to hold true, and which is the case where lambda is less than or equal to 1. As long as lambda is less than or equal to 1, it is consistent with our intuitive process that says wind is flowing at some speed, the blade cannot go faster than that speed or something like that, right. But for other designs the movement is different, and as a result the process is different, as a result you are able to create this situation where the tip speed is different. In all cases energy is conserved, so it is not, so that is I think the more fundamental aspect that you have to remember. You should not worry so much about the velocity, you should be stuck on this idea that how can that velocity be higher than this velocity. That is not the defining characteristic in this case in many of these windmill designs. What is more important is the energy is conserved. So what the in terms of the movement of the windmill, whatever energy it has picked up is going to be less than or equal to the energy that the wind in fact it is going to be less than the energy of the wind that arrived at the windmill. It is never going to be even equal to that energy, right. So it is going to be less than that energy. As a result, that is the characteristic that we should feel satisfied has been met in this situation, and as long as that characteristic is met, whatever is the velocity that ends up being there in the windmill is fine. I mean, so we need not worry that that velocity is not matching this velocity, etc. That is not how it works. The energy conservation is the more fundamental defining idea, right. So that is the way you should think about it. Okay, so we spoke, I spoke in the just now about the idea that you have different designs of windmills, and based on the design you may actually have the tip speed ratio which is greater than 1. Right. So that is the idea that I am pointing out here. So there are certain types of design of movement based on flow. Okay. So here we have flow of wind, and based on that you have movement of the windmill blades. Okay. So some of these movement of windmill blades happens. I mean, again this is based on the design of the windmill. Based on the design of the windmill, you can design the windmill such that the movement of the blade occurs due to a phenomenon referred to as lift. Okay, so it occurs due to a phenomenon referred to as lift. Okay, this is the same lift concept that is there when a aircraft is trying to take off, or even when it is flying, right. So as it is flying, it is the same concept that exists. There is a lift process which pushes the aircraft up, and that is how the aircraft takes off, okay, and then stays in the air. So lift is very critical, it is a phenomenon, a very important fundamental phenomenon that exists in the context of aerodynamics, and this is the same concept that is being used in certain windmill designs. So what it is something that we are just going to briefly look at. What you see here on your screen is an aerofoil. Okay. So based on which part of the world you are looking at, some places they will simply refer to it as airfoil, but more specifically we call it aerofoil. So you can see this shape, this is a shape that I have drawn here. So a schematic of a shape, this shape is the cross section of a surface of a object, and if the object has this kind of cross section and it is interacts with wind, it tends to create this lift. Okay. So for example, aircraft wings, if you look at aircraft wings and take a cross section of the aircraft wing, So, if you have an aircraft wing that looks like that, right. So, you have this aircraft wing and you take a cross section of it. So, you cut the aircraft wing there, right, you cut the aircraft wing there and you take a cross section of it, then it will have this shape, this exact shape that I am showing you here, something of that nature. So, it will have a shape that looks like that. Okay, so, some shape like that is what the cross section of that aircraft wing will look like. Similarly, we have this windmill blades. So, you have a blade like that and you have a blade that looks like that, I mean that is the hub and then you have a blade. If you cut this here, so we just cut it out here and you take the cross section and then you look at the cross section, then this is what you will see. Okay, so this shape is referred to as the aerofoil shape. Okay. So, what happens? So the point is in this kind of a circumstance and similarly with the wing of a plane, what you are seeing is if you see the aircraft. So, I just draw a schematic of some aircraft here and then you have the wing, right. So, you have some wing there. Now, you must remember that the breeze, as the aircraft moves forward, the wind is actually coming in this direction. Okay. So, this is the direction in which the wind is coming because the aircraft is moving in this direction. Okay. So, even if it is on a stationary day, the engines of the aircraft switch on and then the aircraft moves forward. Okay. So, it moves forward, gains speed on the runway, it is picking up a lot of speed and it, let us say it crosses some 300-400 kilometers an hour, something like that, it is picking up some pretty good amount of speed. So, at that point relative to the aircraft the wind is coming backwards, right. So, the wind is coming backwards. So, what happens, the aircraft lifts off the ground, right. So, the lift happens in this direction. Okay. So, the wings are helping the aircraft to move in that direction. Okay. So, that is the lift. On the other hand, the wind is also rubbing against this aircraft and that sort of like you can think of it as friction which is holding the aircraft back. So, there is a force in this direction that is called drag, this is called lift. Okay. So, this is upward direction, what is happening is lift, what is pushing the aircraft back is drag. Okay. Now, the point you must notice here is that the wind is flowing in this direction, the lift is happening in a perpendicular direction. Okay. So, that is an important thing that you have to remember. The lift is not happening in the direction of the wind, the lift is happening in a direction perpendicular to the wind. So, that is a very important thing to keep in mind. So, now if you keep that in mind, and that is exactly what is happening in on an aircraft wing which I have shown here, that is also happening on the blade of a windmill of the design that I have just shown you, those 3 blade windmill designs that I just showed you, which is a horizontal axis windmill. So, in those designs the breeze is moving horizontal to the ground with respect to the ground, the blade is moving in a direction perpendicular to the breeze, right. So, exactly the same in terms of directional orientation that is consistent with what I am just showing you for an aircraft. So, what is happening? So, what is so special about this shape? So, there is this thing called the aerofoil shape and that is what you are seeing here. So, what happens is you have a lot of let me just take some other color here, so it is easier for you to follow. Okay. So, we have some color here. So, you have let us say you have breeze coming. So, this streamline will go off this way, that will go that way. Okay. So, you will have a lot of breeze that is doing this. Okay. So, now generally what is happening here is that the path travelled by the air molecules on top of the aerofoil is longer than the path travelled by the air molecules at the bottom below this aerofoil. Now, there is some analysis that people do and there are different approaches to looking at this. So, one approach basically says that let us say you have 2 molecules here, one molecule here and one molecule here. So, then they look at what is the path travelled by that molecule on top to arrive here and the molecule at the bottom to arrive here. And so, one sort of assumption or assumption that is made is that they both arrive here, they both start at the same point and they arrive at the same point at the same time. Okay. So, the starting point is similar and the finishing point is similar, and one assumption is that they all arrive at the same point to ensure continuity. So, if that is the case, then the path travelled on top is longer than the path travelled at the bottom. So, therefore, the velocity of the wind above this aerofoil is higher than the velocity of the wind below this aerofoil. Okay. So, that is one approach, although some people are suggesting that actually the velocity in fact these particles on top may even be coming faster than that. So, that is another angle you can think of, but that simply adds to this process, not subtracts from this process, but the general assumption is that they are all arriving at the same time. Even when they are arriving at the same time, you are going to see some difference. So, the idea is that the velocity on top is higher than the velocity at the bottom of the wind. So, now if you look at fluid flow and you look at the idea that energy is conserved, okay, so that is the again the underlying phenomenon that I said, that is the phenomenon that we should tie ourselves up to, and within the context of that phenomenon whatever happens happens. So, we looked at Bernoulli's principle. So, in Bernoulli's principle we said half rho v square plus rho g h plus P equals a constant, right. So, in this context we basically said that this is the kinetic energy per unit volume. So, this is K E per unit volume. This is potential energy per unit volume, and this is of course pressure. I showed you that the dimensions of kinetic energy per unit volume and potential energy per unit volume, which is basically energy per unit volume, is the same as pressure. So, therefore, this equation is appropriate and correct as per dimensions, and this says that this is a constant. So, if you look at situations where let us say you are basically not worried about the change in height, because the the breeze is flowing at the same height, let us say between the starting, I mean if you compare the starting point and the end point, there is no great variation in the height, they are essentially the same location. So, we can forget about or we can neglect potential energy per unit volume, because that is the same both at the starting point and the end point. So, we basically have only two terms here, half rho v square, and so let us say this is path 1 which is coming on top and path 2 which is coming at the bottom. So, half rho v1 square plus p1 should equal half rho v2 square plus p2. So, this is p2 comma v2, where v is the velocity here, not volume, velocity here, and then on top you have p1 and v1, which is the velocity on top. So, if you have created a situation, so given that this has to be conserved, you have this equation here that has to hold as part of energy conservation of this fluid flowing around this airfoil. If this equation has to hold, then whenever the velocity goes up in any one location, correspondingly the pressure goes down. Okay. So, to the extent that we find that in pathway 1, because the distances travelled have to be longer, and it turns out that if you actually do the proper calculations and you understand all the dynamics that is happening there, the velocity in that path 1 for the molecules happens to be much higher than the velocity in path 2. Therefore, we find that because of the shape and how it is interacting with the breeze, V1 happens to be greater than V2, and how much greater it is will depend on exactly what assumptions you make and how correct those assumptions are. So, usually the assumption made in most places when they discuss this is to say that the molecules start off at the same point and they end up later also at the same point, and therefore they simply look at the path travelled, that one travels a longer path in the same duration of time, the other travels a shorter path in the same duration of time, and therefore the velocity of one is greater than the velocity of 2. But like I said, some people actually say that there is some analysis which suggests that it may even be the difference may be even more than that, not just simply based on what is there when they both meet up there. So in any case, the velocity is higher. There is no two opinions that the velocity is higher. Because the velocity is higher, the pressure is lower. So if pressure on top is less than the pressure at the bottom, so if P1 is less than P2, then what happens? Pressure below that aerofoil is more than the pressure above the aerofoil, right. So velocity 1 is greater than velocity 2, and as a result pressure 1 is less than pressure 2, pressure 2 is below the aerofoil, pressure 1 is above the aerofoil, and since you have low pressure on top and higher pressure below, it pushes that wing up, it pushes the wing up because you have this difference in pressure, right. So that is how the lift is generated, and that is the process by which you get the situation where breeze is flowing in one direction, the movement is happening in a perpendicular direction. Okay, so that is the point in with this design, right. So with this design, breeze is flowing in one direction or wind is flowing in one direction, movement happens in a direction perpendicular to it, and that is the way in which this aerofoil as a result of the pressure difference between the bottom and the top, because more pressure is at the bottom, less pressure is in the top, it gets a lift. So you get lift. Okay, so this is the idea, and whenever this movement is based on lift and you have this windmill where this movement is based on lift, then you do not have to worry about this exact relationship between the two velocities. You end up having a situation where the tip of that windmill is actually having a velocity higher than the breeze that is flowing perpendicular to it, and of course energy conservation takes care of all other issues associated with it, and you get values of lambda that are greater than 1, and like I said, it could even be 4, 5, 6 etc., which can be significantly greater than 1. Okay. So this is lift based design, and most of these 3 blade windmills that you see, which you see along in many places in India, at least these days you see it, those are all consistent with this kind of thought process and analysis. So lift based design, for example, would be this is a standard design that I think we are all familiar with, which we see in many places. There is also, but this is horizontal axis. Horizontal axis wind turbine. So sometimes they write it in as an abbreviation HAWT, horizontal axis wind turbine. What you have here is another wind turbine which is referred to as the Darius wind turbine, and it is a vertical axis wind turbine. So that is also okay, so that is VAWT. In this particular example, even this is vertical axis, so the axis is in this direction, the blades are moving in this direction, but in this case also the blades are designed such that the movement occurs due to this lift phenomenon. Okay, so it is not occurring due to another phenomenon which I am just going to discuss in our immediate next slide, which is the drag design. This is still based on lift. Okay, so lift based design is what you are seeing here also, and it is a slightly twisted kind of blade, that is why you see this difference in shading as you go from the top to the bottom. So it rotates this way, and it is also still based on lift, and so for this also the lambda can be greater than 1. Okay, so this is what we are looking at. Now the other design that I told you, which is perhaps the older style of windmill design, some of the early windmills had this design that they looked at, which is called the drag design, and the Savonius wind turbine is a particular style of the drag design, which is what you see here. So again, this is also a vertical axis wind turbine. Okay, but there is a big difference here. So here the wind is flowing in this direction. Okay, so in both places it is flowing this direction, but when it comes to this surface, it just slides past the surface and also still gathers up here. So, you end up getting more push on the right side of this wind turbine, less push on the left side of the wind turbine. So, but the point is it is based on a pushing action. So, the wind is physically pushing the blade that is directly ahead of us. So, the blade basically moves in fact in the direction of the wind. So, it is first getting pushed in the direction of the wind, and then because it is stuck on a on an axis, it rotates away, but fundamentally the action is being pushed. Okay. So, now or rather that is why this term drag is used, push or drag, that is pushing the wind turbine away as it physically pushes it away. Now, the important point you have to remember here is that the tip here, the tip of this wind turbine, as it starts moving, when it is getting its maximum thrust, is moving in the exact same direction as the wind. Okay, so, the tip, this is V tip and this is V wind. So, that is the direction of the wind and that is also the direction of the tip. Okay. So, now the air molecules are physically pushing the wind turbine in the direction that they are moving. Now, clearly the only source of energy there is the velocity with which that the kinetic energy of those wind molecules that have come there, and so they are coming with some velocity, and they with that velocity they are pushing this surface that is ahead of them. So, clearly that surface cannot move faster than the rate at which those molecules are coming and pushing that surface, right. So, in this design, this flat surface or this curved surface in this case cannot move at the tip of that curved surface, cannot move at a velocity faster than the velocity with which this wind is flowing, because this wind is directly pushing this surface. There is no lift involved here, there is pushing action that is involved here. So, in this case, if it attempts to go faster, then it is no longer get any thrust from the wind, then it will lose the ability. So, even for a moment if it were to go faster than the wind, it will pretty much there will be no further push, it will slow down till the wind catches up and wind will keep pushing it. So, even if you hypothetically consider that situation, so you put it in the wind and you turn it faster than the wind, it will slow down and it will go only at the wind velocity. So, if you use your hand and you rotate it much faster than what the wind can do and you just leave it there, in a few seconds it will line up with the wind velocity, it will not be able to go faster than the wind velocity. So, in this case the tip V tip can only be equal at most maximum that it can be at its maximum can only be as much as V wind, okay, and that is because they are both moving in the same direction. So, that is the big difference. When you had the lift design, they were not moving in the same direction, and so the relationship was very different, and Bernoulli's principle defined what could be done there. Even here there will be energy conservation, etc. So, that it is not that this is in violation of energy conservation, this is also associated with energy conservation, but there are additional restrictions because of the fact that there is a push design involved, it is not a lift design, and as a result the V tip at most at its maximum can only be as much as V wind. So, typically V tip is less than V wind. So, therefore, you have this tip speed ratio being less than 1. Okay. So, now this is the idea that we have to keep in mind, and this is important sort of in the context of the windmill designs. So, now that is a concept we will keep in mind, we will use it as we find necessary in the design discussion. So, let us look at number of blades and let us say to what degree this tip speed ratio or TSR we will call it, tip speed ratio, we will call that as TSR. Let us just see to what degree this TSR is of any consequence to us. So, typically we have 3 blades and it is rotating. Our most common application is power generation. So, that is why it is also being referred to as a wind turbine as opposed to simply calling it a windmill. Now, the point we have to remember is that as the blade rotates, so let us say it is rotating that way. Okay. So, wind strikes a blade and as a result of wind going past the blade due to a lift action, the blade moves away. Now, as the blade moves away, it has locally disturbed the wind, right. So, there has been an interaction between the wind and the blade, and that has resulted in some disturbed wind. So, some turbulent wind is there. So, you had some smooth wind going, you had some turbulent wind. Now, if you have the next blade of the turbine arrive at that spot before this turbulence goes away, then the next blade cannot completely benefit from the flowing wind. Okay. So, what to restate, the wind interacts, we just say wind interacts with blade, generates lift. Okay. So, that is the first thing that happens. So, what happens? Blade moves away, and at the same time wind has been disturbed, wind in that vicinity, in the location of that blade, where that interaction happened, no, in that vicinity, in that region of that, near that region, wind in that vicinity has been disturbed, and at that point it is not smooth, it is kind of turbulent because it had that interaction. So, it has been disturbed. So, blade moves away, but it will take maybe a few seconds, some amount of time is required for wind at that location to restabilize. Why it restabilizes? Because wind is coming, fresh wind is coming, then wind is coming from a long distance, right. So, it has some stable properties, some velocity, some smooth flow that is happening, that is coming, with which it is coming. So, now you had a blade, that blade interacted with the wind, it got pushed away, but in that process it sort of messed up the wind there. But if you give it a few seconds, this messed up wind will go away, fresh wind will arrive here, which will be the same as whatever the original wind that interacted with the blade. So, you need a few seconds before this blade moves away and this fresh wind arrives at that location. Okay. So, some amount of time is required. So, it is a finite amount of time, usually a matter of seconds, maybe fractions of seconds to a second or a few seconds before the wind will restabilize at that region. So, if I call this region A, okay, so and let me call this blade B, call this as blade C. So, this blade A will move away, but this particular location, let me call this location as L. Okay. So, blade A is at L, because of the interaction it moves away. Now, blade B is also going to come to the same location L. By the time the blade B arrives at L, we want the wind to be stabilized at the location L. So, we say wind interacts with blade, generates lift for blade A at location L. Okay, blade moves away and wind in the vicinity has been disturbed, in that vicinity has been disturbed near around L. Some amount of time is required for wind at that location to restabilize at L. So, this restabilization we want at L. So, then 4, by the time blade B arrives at L, wind should be stable there. Okay. So, this is the kind of thought process that is here. By the time the blade B arrives at L, the wind should have restabilized at that location L. Now, the point is, if the wind has not restabilized, it does not mean that your windmill will stop operating or that it will stop generating energy. It is just that that process will not be efficient. You will actually lose energy. You are not capturing all the energy in the wind. The wind has much more energy. You are capturing disturbed energy, only some part of that energy you will capture from the wind. You are not capturing all the energy that is there in the free flowing wind. So, the better design is such that you want to set it up such that the tip speed ratio is such that by the time that blade comes to that location vacated by the previous blade, the wind has restabilized. Okay. So, that is how we do this calculation. So, if you want to extract the maximum power out of that is available in the wind, we need to consider the tip speed ratio of this windmill, and based on that only we decide how many blades are possible. Okay. So, if the tip speed ratio is high, then you can use less number of blades. Okay. If you use less number of blades, then just let us say, so you have less number of blades. So, for example, let us just look at this, we will look at possibilities here. So, we could have 2 blade design, we could even have a 1 blade design, we will just talk about this. So, we have a 2 blade, 3 blade design, 2 blade design, 1 blade design. So, supposing the tip speed ratio is some value V1 in this case, and V2 in this case, and V3 in this case, these are tip speed ratios. So, if the tip speed ratio is some value V1 which is medium, you want it such that in that at that velocity, by the time it comes here, this the wind has stabilized here. If this tip speed ratio is higher, then you need the blades to be further separated. So, a two blade system would work. So, this tip would work, travel this entire distance before it comes here, and by the time the wind would have stabilized, and of course, in this case this will travel the full circle and come right back here, right. So, that is the full circle that it is going to do to come right back to that starting point. So, the higher the tip speed ratio, you can get away with lesser and lesser number of blades. The lower the tip speed ratio, you can, if you wish, use more and more blades and still capture more and more energy from the windmill. So, in principle you can have a 3 blade design, 2 blade design and 1 blade design based on tip speed ratios, and also you have to keep in mind that if you are using this primarily for generating electricity, then having higher RPMs is what is more useful to us. Generally the torque requirement is not as high, whereas the RPM requirement is much higher. And therefore, high tip speed ratios is important because that decides the RPM. The faster the tip is moving, you will have a higher RPM, right. So, generally these designs are based on that thought process. You should also keep in mind that as the blades move, ever so often one blade will line up with the tower. So, you have a tower here. So, that blade, the instant that it is lined up with the tower, it is not going to face the same kind of environment that the other blades are facing. So, usually the blade that is in front of the tower actually has a disturbed kind of behavior relative to the other blades, and that affects the stability of this wind turbine, affects the stability of this whole process. So, if you have only 2 blades, you have one blade facing a drastically different situation compared to the blade that is diametrically opposite to it. Every time the blade is one of the blades is lined up with that tower, right. So, that is a very unstable situation relatively speaking. So, 3 blade designs in that sense are considered to be very good because you have 2 blades which are sort of stabilizing the wind turbine when only one blade is facing this circumstance of the tower, okay. So, of the involvement of the tower. So, generally 3 blade designs are preferred. 1 blade design can also do the job, you simply have to have a counterweight here. Can also do the job if you are only interested in looking at RPM, if torque is not an issue. If torque is not an issue, one blade design can also, at the end of the day, that blade also is rotating as a result of the interaction with the wind. So, it will also have the same tip speed ratio and or something to that based on that behavior of the wind interacting with that blade. So, you can get the RPM using one blade also, but generally this is considered very people wherever this has been installed, although functionally it works fine, it is considered as something that a lot of people object to because it seems to affect them to see this single blade rotating. So, it is actually a more psychological reason why people do not use this design. It seems to bother a lot of people to see this single blade repeatedly rotating in the sky there. Something about that is very disturbing to a lot of people when they see it in action. It is not something that seems to fit with our psychology of what we are expecting in nature, and therefore a lot of people object to this design when it is put up. So, there is no real objection to 2 blade designs and 3 blade designs. In that context, the 3 blade design seems to have a good mix of various factors taken into account. The stability, the dynamics of the whole process, etc., seems to come off much better with the 3 blade design. So, that is what is commonly used. And like I said, if torque is important, where you are where you do not mind the speed of the windmill, but you are more interested in torque. So, RPM is not important, but torque is important. Then having more blades is useful because you are able to get more energy from the wind that is going through that process and then push that use that to generate that torque. So, the older design windmills which were primarily aimed at grinding things or pumping up water, where torque was a critical thing, they typically have more blades that are put up. Okay, so, while we have discussed all this, I would like to finish up this class by looking at a completely alternate design for windmills, and which is going to be quite surprising for you, and that is referred to as a wind tree. So, what I want to draw your attention to is the fact that people are looking at totally different designs. So, what you see here looks nothing like a windmill, right. So, one of the objections to the windmill is that you have these huge structures which are blocking up space and are blocking up your view. I mean you go to a nice beautiful landscape, you look around, you would like to say let's say you go into the sand dunes of Rajasthan or some place, and some lovely place you go, you want to see nature in pristine condition. You see the nature, and then ever so often you see this big windmill that is parked there, which is not natural. I mean you see this huge man-made object that is parked there. It seems to become an eyesore, so to speak, in that landscape. And the more you deploy these windmills, you are going to see more and more of them. So, people have come up with some interesting design where it does not even look like a windmill. So, it just looks like a tree. So, I mean of course, this is colored artificially just to give you an idea of what is expected here, but basically what you have here, you have a series of vertical axis, small vertical axis windmills, wind turbines. These are all vertical axis wind turbines, and clearly you can make this is just a schematic, you can make like a tree with several branches that looks very natural, and you can set it up in streets and whatnot, or in some open parking areas where there is enough breeze blowing. And so, these windmills are actually rotating this way. Okay, so, that is how they are rotating, and in that process they are generating electricity. So, instead of having one large wind turbine, you have a lot of small wind turbines which are continuously interacting with the breeze and generating electricity, and the whole thing looks nothing like a like a wind turbine, and it actually distributes, it makes the whole deployment process very easy. You do not have to create this huge massive structure that you have to go and put up. In many ways it is not very different than putting up a lamp post. So, you can put up a lamp post, on top of it you can even put up this tree if you want, and you can keep generating electricity. So, this is a very lovely concept, and since this is not solar power, you can do this during day, during night, etc., and it works absolutely fine. Okay, so those are the interesting design aspects that I wanted to discuss today as we close our discussion on wind energy. So, in conclusion, I just wanted to say that the lift based design is more efficient than the drag based design, and it is able to have tip speed ratios higher than 1 and is able to capture more energy than the drag based designs. For power generation, RPM is important. And even one blade may be sufficient if torque is not important and only RPM is important, one blade may be sufficient. For other mechanical purposes, torque is very important, and in that case multiple blades may be desired. In any case, in all these cases you want to check what the tip speed ratio is, and then understand that you are not overdoing the number of blades, that you are actually effectively using the interaction between the blade and the wind. So, that is something that you have to look at. And finally, that I just showed you that there are very interesting alternate designs. You can actually check on this in the internet. They have a lot of videos on this kind of wind trees. You can easily just search for it. You will see videos or animations of those wind trees. They look very nice. They look very similar to trees, and maybe you can design one with that looks almost exactly like a tree, and then generate wind. So, that's alternate designs are there. People are looking at all those alternate designs, and so. If you look years down the line, if you say suddenly wind energy is either everything or a very significant fraction of our energy supply, then you may have all these kinds of interesting gadgets distributed across our cities. So that is something that we can look forward to. So, in any case, with this I would conclude this class and also our discussion on wind energy. In subsequent classes we will look at other technologies. Thank you.